Hello everyone and welcome to today's webinar about signal integrity of high-speed integrated circuits. My name is Amin. I am RF Application Engineer at EMWorks. This is a brief overview of the presentation. So first we'll talk about trends in integrated circuits and package technology. Following that, signal integrity and some simulation results will be presented. At the end we have a live demo. So in case if you have any question, I'll be happy to answer them at the end of the presentation. Alright, so now let's talk about the trends in integrated circuits. Advanced integrated circuit technology allows downscaling of chips and the integration of large number of transistors on a single chip. It also results in small form factor and high performance in-chip package systems, as well as faster data communication. On the right hand side, we have an image of two common integrated circuit technology, namely SoC, system on a chip, and SAP, system in a package. In SoC, the components are in single chip and are spread over the chip. On the other hand, in SAP, the components are in different chips, and also the chips are stacked on top of one another, and this helps save more space as compared to SoC. SoC, it's more like a complete computer system on a single chip, which is capable to perform complex tasks which have higher resource requirements. SoC, it can be used in mobile computing, such as tablets, smartphones, smartwatches, and notebooks. SAP, it can be used in devices such as smartphones, digital music player. Alright, so now let's talk about the package technology. There are several package technology, but today we'll be focusing only on the common and the most advanced package technologies. So basically we'll be talking about the following packages: wire bonding package, flip chip package, 3D TSV package. Traditionally we have what we call the wire bonding technology. In this package, the die is connected to the package substrate through wires, as we can see in this image. On the other hand, in flip chip package, the active surface of the chip is flipped over facing downward. The chip is connected to the package substrate using the solder bumps, which are underfilled with epoxy. The use of flip chip package allows a large number of interconnects with shorter distances as compared to the wire bonding. Also we have what we call the 3D TSV package, or through silicon via, and this is one of the most advanced package technology. Traditionally we have the wire bonding in this technology. So basically the chips are interconnected through wires, as we can see in this image. In TSV package, instead, the chips are stacked on top of one another and they are interconnected through silicon via. The use of 3D TSV technology results in higher I/O densities, more complex interconnects, and reduced size of a package. Alright, so now let's talk about signal integrity in high-speed ICs. Over the last decade, the frequency of local clocks on chips and the speed of I/O drivers have continued to increase, and this gives rise to signal integrity issues. So what do we mean by signal integrity? Signal integrity simply means the ability of the signal to travel from the transmitter to the receiver without distortion. Signal integrity looks at two main aspects: the timing and signal quality. And basically it tries to answer two main questions: does the signal reach its destination within the given time limit? Also, when it reaches its destination, is it in good shape? So for example, on the image on the right hand side, so we can see transmitter, the channel, and the receiver. So at the transmitter we can see a clear eye, unlike the receiver where we have almost a closed eye. So now it's really hard for the receiver to distinguish between bit 1 or 0. Looking at the bit pattern, So for example, for the transmitter, we can see small distortion, unlike the receiver, we have like a bigger distortion. So we can, looking at the bit pattern of the receiver, we can see signal attenuation as well as ISI, or inter-symbol interference. Alright, so let's talk about some factors that are responsible for signal integrity issues. There are several factors that contribute to signal degradation. These include impedance mismatch, crosstalk, EMI, attenuation, and propagation delay. Signal attenuation can cause several problems such as inter-symbol interference, or ISI, bit errors, lost data packets, and others. In the next following slides, we'll be explaining briefly each of these factors. So now let's start with the impedance discontinuity. When the signal travels through the channel, it sees impedance discontinuity, and this could be because of changes in signal routing layer, via holes, and antipaths. Impedance discontinuity can cause reflection noise, which in turn increases time delay and produces overshoot, undershoot, and ringing. In this image on the bottom right hand side, so we can see, for example, for logic 1 there is the overshoot. So now it becomes very hard for the receiver to distinguish between logic 0 and logic 1, as this is now happening beyond the specified value region for logic 1. The same thing for the logic 0. The via holes and antipaths can be modeled as a pi circuit, as we can see from this image. On the left bottom hand side, we can see a diagram of single via. So in this image, we can see the via, the antipaths, as well as the routing layer. So we can see a different impedance discontinuity. Alright, so let's talk about crosstalk and EMI. Crosstalk and EMI are the two major source of noise in integrated circuit. There are mainly two mechanisms that causes crosstalk and EMI. This is the mutual inductance and the mutual capacitance. When the current passes through a conductor, it creates alternating magnetic field. The varying magnetic field, it can either radiate electromagnetic energy causing EMI, or it can get coupled to the nearby conductor, resulting in crosstalk. Similarly, for the electrical voltage, when the electrical voltage passes through a conductor, it creates a varying electric field. The varying electric field, it can either radiate electromagnetic energy causing EMI, or it can get coupled to the near conductor, resulting in crosstalk. Crosstalk and EMI, they can cause several problems, such as loss of synchronization between data and clock signals, as well as signal propagation failures and pulse distortions. Alright, so now let's talk at the attenuation and the propagation delay. When the signal travels through the channel, it gets degraded because of the resistance of the PCB traces and also the board dielectric losses. The attenuation, it can lead to problems such as slow signal raise times, as well as increases the possibility of data errors. Also, we have what we call the propagation delay. So for example, for the lossy FR4 material, it has a dielectric constant of 4.7, which is constant up to frequency of 5 GHz. When the frequency increases beyond 5 GHz, the dielectric constant of FR4 drops to 4. So this means that different frequency components of the FR4 material will have different velocities. So eventually they will reach the destination at different times, and this causes the signal distortion or propagation delay. Propagation delay can lead to signal skew and also signal sampling errors. Alright, so now let's talk at some ways to minimize the signal integrity issues. To minimize the reflection, the impedance of the source, receiver, and signal traces should be matched. The use of low-loss dielectric and metals, it can help reduce the signal attenuation. To reduce crosstalk, there are several ways. These include providing adequate separation between the traces, use of ground planes, as well as differential signals, as this is less sensitive to the effect of crosstalk. To minimize the electromagnetic interference, proper grounded should be used to achieve the shortest current return path and the shortest current loops. The use of solid ground planes next to the power or signal planes is one of the common practices to solve the signal integrity issues. Alright, so now let's talk about how signal integrity analysis is done practically. So for the signal integrity, basically we have two main steps. First is the I diagram, next is the S parameter. I diagram is a quick way to find out about the signal distortion happening in the channel. Next, we have the S parameter. So for the S parameter, we can use it to identify the root cause of the signal degradation. Sometimes we can use what we call the TDR, and TDR, it can be used to find exactly the impedance discontinuity in the channel. So for example, looking at this image at the bottom hand side, so we can see at time of 1.1 nanosecond, so we have impedance discontinuity. So now since we know the speed and the time, so we can find where exactly in space or where exactly in the channel the discontinuity is happening. On this image at the bottom left hand side, so at the receiver we can see clear open eye. So as the signal travels through the channel, it gets degraded. So at the receiver we can see almost closed eye. So now it becomes very hard for the receiver to distinguish between logic 0 and 1. So by looking at S parameter, so we can find out about the reflection coefficient as well as the signal attenuation. So by looking at, for example, at S11, so we can check for return loss, and by looking at S21, we can find out about the insertion loss. Alright, so before we said that the S parameter, it helps us identify the root cause of signal integrity. So for example, by looking at SDD11, so we can find out about the reflection, while looking at SDD21, it can help us find about the signal attenuation. SCD21, it gives us information about electromagnetic emission, while SDC21 gives us information about electromagnetic susceptibility. So by looking at the values of this parameter, it can help us identify the root cause of signal integrity issues. Alright, so today we are going to study the signal integrity issues in flip chip package. So basically we are trying to find the effect of the interconnects, the via, and the material on signal integrity of the flip chip package. On this package, so we have the differential signal, which is traveling from the test IC to the PCB through C4 bumps. Okay, so now let's look at some simulation results. On the top hand side, so we can see a picture of the simulated coupled microstrip lines. At the bottom, we can see the animation of electric field. So we can clearly see there is a strong crosstalk. Looking at both two graphs on the left hand side, so we can see that both the near end and far end crosstalk are not a major concern at low frequency, but as you go higher in frequency, so both crosstalks becomes a significant factor to consider. By providing appropriate spacing between the traces, so it can help reduce the crosstalk. Alright, so let's look at the effect of the VS and the material. On the right hand side we have a picture of the package with multiple VS. On the left hand side you can see the animation of the electric field of the package. Alright, so let's look at the effect of the VIA. Looking at both two graphs, the insertion loss and return loss, we can clearly see that the VIA acts as a low pass filter. By increasing the VIA diameter, or in other words increasing the VIA aspect ratio, it helps reduce both the insertion loss and the return loss. Now let's look at the effect of the material. So in this example we want to study the effect of three materials, namely silicon, glass and Rogers 48050B. From this insertion loss figure we can see that the three materials have almost the same performance up to 2.5 gigahertz. But as we go high in frequency, so the losses in the silicon become significantly higher. Also from this graph you can see that the glass has the best performance as compared to the silicon and Rogers 48350B. Also in HFWorks we can also see volume loss density in the structure. For example, in this example, so we can see the volume loss density in a package. So here we can, for example, see the conductor and the dielectric losses in a package. Alright, so let's do some time domain and frequency domain analysis. In this example we'll study the effect of the use of silicon as well as the use of glass. So as if you remember from the previous analysis, we said that the silicon has high losses as we go high in frequency. On the other hand, the glass has lower losses as compared to the silicon. So for example, by looking at the eye diagram for both receivers, for the glass and the silicon, so we can see for the glass it has less attenuation as compared to the silicon, and this can be also clearly seen from the bit patterns from through glass via and through silicon via. So for example, in through silicon via or TSV we can see there is like more attenuation compared to the TGV or through glass via. So here we can see that by for example, when we see the oscilloscope, when we see both the eye diagrams of the both receivers and looking at the bit patterns, so basically we can only say that there is problem in our channel. But by using the electromagnetic simulation software, it can help us identify the root cause. So for example, from the previous analysis we have seen that, for example, the V8 can has an effect, the material, as well as also the spacing. So doing the time domain analysis is simply not enough, so we need to use the frequency domain analysis through the use of electromagnetic software. So from this example we have shown you how HFO can help us identify the factors that causing the signal degradation of the high-speed IC. Now we'll have a live demo. We'll be showing you how we can design and simulate the signal integrity using HFWorks. Alright, so this is HFWorks and this is SolidWorks. HFWorks is fully embedded in SolidWorks. Also, HFWorks is gold certified by SolidWorks. So once you are done creating your geometry in SolidWorks, you can just go ahead and start your simulation using HFWorks. In HFWorks, we have 4 types of study. We have antennas, S-parameter, TDR, and resonance. So for each study, almost we have 3 main steps. So first we need to, for example, here we need to specify the type of accuracy, the frequency range, the type of mesh, is it manual, is it adaptive, and also we can do some thermocoupling analysis. So once we